and you can ask anything that you want. If it's related to Exascale or not related to Exascale, we'll bring it up together. So I'm gonna shoot a few questions, and feel free to comment, by the way. Bring your own opinion, or ask questions from your side as well. Rich, how we're gonna do it?
I'm all set.
You're all
I
set.
got 2 microphones. We're good.
Okay.
Yeah, 2 turntables in there.
Okay. So we have been doing those panels in the last few conferences we're doing, and I kind of used to ask the same question over and over, and I think I'm going to ask the same question here just to kick it up. So for the folks that participated in the panels before, I'm sorry, but you probably know the answers, so it's going to be easier from that perspective. And you might have changed your mind from the last time. So the first question is talking about Exascale, right? We are talking about Exascale. I have my own view what Exascale is, but it's still an open term, right? What we talk about Exascale, but from your perspective, what is Exascale? And you can go one by one. Dickie, you can start, or send.
Yeah, I think Exascale, in reality, it will be like if there is a machine which can deliver the real performance for a real application, not just top 500 number, LINPACK number, but an application which can actually deliver exaflop or around that kind of a target.
So if someone's gonna announce the first exaflop machine measured by LINPACK, is that the time we enter Exascale, in your opinion, or not yet?
Yeah, I think, from a marketing side, I think people will definitely say that is an Exascale machine. But will that be really useful for all applications? That is the scientific side. So we need to distinguish between what is the scientific side versus what is the marketing or business side.
So, yeah, I think I'd basically agree with you. But I wouldn't say one LINPACK exaflop is an Exascale machine. I would think that would have to wait for real application to execute an exaflop, although it's going to be perceived as an Exascale machine because that's the way the company or organization is going to talk about it. But
yeah, I really don't have anything to add here.
Neither do I. The only thing I would say is an Exascale system is a terascale system a few years ago. So we are just only moving with time. That's definitely a simple description.
Okay. Do we have the speaker from DDN here?
They are in a meeting.
Sorry?
They are in a meeting.
Okay. So, Hussein, you talk a bit about storage, so I might throw the question for you instead of DDN. When we talk about Exascale, it's we're more talking about the compute side, right? But what about the storage side? Do we need to look into exabytes, or storage? It's not part of Exascale terms.
So I think the complete system starting from the computing to the network and to the storage. Exascale is going to be the most challenging part will be just really having a balanced system between these 3 components. And I believe the lacking is not only the storage. Storage is one of the parts that's lacking. And if we look at the numbers that DK today announced, this number of times we would like to be able to reach the Exascale, it's not going to be easy with the level of consuming. The storage part is using the same component of the computing, so we are talking about the same processors, the commodity processors, the same interconnects, so definitely they will be facing the same problem. So I won't divide it from any computing or interconnect problems and limitations.
Okay. Any question from the audience before I'm going to jump to my next one? Yes, please.
Do you think Exascale is actually possible? Exascale is actually possible in, let's say, 5 years from now, taking into account the limitation in computing power, consumption, real applications. I don't mean LINPACK, I mean real application right now. Or we need to think in a completely different hardware from what we have now, and completely different software.
I think the answer lies, you indicated the power. I think if we remove the power constraints, I think the target will be achieved much more quicker. Components are there, software stacks are there, it is a question of money, whichever country wants to put it together. But if we are thinking of the power, then I think that will require some time. And that requires the hardware innovation as well as the software innovations, and then completely evaluating the complete machine and the stacks. And there we may see that it may go a little bit beyond. That's why that horizon earlier it was 2018, in fact, people were talking about, and now it's gradually has moved to 2020, 2024. So it'll happen like that. So I cannot predict anything, or neither anybody else can predict.
And I think there's also this distinction between a small number of applications running, which I'm sure will make it, and a wide range of applications, which historically always takes 10, 15 years for a wide range of applications to catch up.
Yeah, I was just going to say, I don't think a specific power metric is going to prevent the first deployment by any great extent. I mean, the first machine or country or organization to reach that. I don't think it's going to care too much about if they miss it by 10 megawatts or even 20 megawatts. If they have a machine, they'll put it online, and power consumption will go down just like as it is in the petascale era. You can get a petascale machine for just a few megawatts now, so it'll work itself out. But the first one isn't going to matter. Nobody's going to say you can't have a machine just because it's over 20 megawatts. Somebody might do it, and they'll just put it up and run it for as long as they have money for it.
So if there is a reason for the co-design, is a power reason. That's the main reason, and that will follow up for application, plus for the way that we generate power. So there'll be a co-design also for the way that we generate power that will be helping in just saving about that.
Yeah, so it's kind of making that question more generalized, and I don't know if you have anything to add, but essentially the question is, what are the gaps, from what I understand? What are the key gaps that you see that need to be tackled in order to get to the exascale? So I think you mentioned power, and you said that power is not the key one, but I think Rich also talking about the application side, which is the software. I don't know if there is anything else you want to add around that, kind of making the question more generalized.
I think all the components, they need to work together. Scalability is important, the fault tolerance, fault resilience is also important. But what we have seen in the past, is that the field has been growing. It's just like Hussein indicated, whatever, like we are talking about Exascale 10 years back, people like us sat in the panel, were asking the same thing about petaflops or teraflops. So I think we'll see things will happen in both ways, like through some kind of a evolution, we'll see the machines becoming faster and faster. Some of these solutions will be resolved. But at the same time, also some outside of the solutions, out of the box solutions will also come out, which may help to move into the Exascale much more faster. Just like, let's say, take an example of GPU direct RDMA, am I right, which you people are working on. 4 or 5 years back, nobody had thought of those things. But once the technology came and people started looking at it, there was a need and people saw that it can be enhanced. So we'll see those kind of solutions will be coming out in the next decade, and which will help putting together these machines.
Yeah, I would say probably hardware is, all the components are probably the least of the problems in Exascale. I think all those problems are going to be solved in some power envelope that's probably going to be somewhat impractical for a year or two. But I don't see hardware as the big issue. I see software for a real application is going to be the more challenging problem. Some of the frameworks and changes in the runtimes are going to need to occur to get an exaflop application. That seems harder to me than the hardware, which I think are on a pretty good path.
could add one point regarding the system, like with the actual technology now, building a system with Exascale, I mean the components, the hardware itself that's available in the system, the quantity and the number of it, that make it impossible with the technology now to manage due for a certain percent of failure at all levels, all components, whatever they are. So that's why changing there is going to be fundamental to be able to reduce that size, because it's doable now to construct it if you have the money, if you have the power, if you have all this, but managing it and scaling with the software part, it's going to be almost impossible.
So about the, we talk about numbers, terascale, petascale, exascale. Do you see that the more relevant change in development is more qualitative going forward, that we would need to react quickly to unpredictable events? How quickly you can get the recommendations, insights, controls from unforecastable, non-batch stuff, that type of computation. Do you think this kind of dynamic capabilities would become more relevant than the number of floating point operators per second for a batch job in terms of what the actual needs for high-performance computing would be in 2020? Are there this type of disruptive qualitative sea changes besides the pure numerical number crunching capacity demand?
Yeah, I can maybe add to that question too. I think the need to crunch more, it's not just the pure HPC, but we're also talking about big data, right? And data is growing exponentially out there, and we today understand that actually we can use data to do more things that we couldn't do before. We see applications like machine learning that are coming out, and Baidu publicly stated that in order to run their machine learning algorithms, they need a 3 to 4 exaflop capacity in a system in order to do it. So there is already application waiting for Exascale. So I think the question here is that, is Exascale just pure flops, or it's essentially also be able to deal with data, be able to crunch data much more? As big data becomes also part of HPC, and it's not just ability to crunch the data, but also do it in real time. Because we know that there are companies today that needs to do things in real time in order to run their business. For example, PayPal, which is from our perspective an HPC case, needs to do fraud detection in real time in order to run their business. So it's not just crunching the data, but also doing in real time, if understood correctly your question.
Yes, probably a good example is that the machine learning, we would need to adjust the data model based on real-time observations, like A/B testing. We would want to react to what we can learn online in a streaming manner. This type of, do you see that this type of surfacing, this type of demand capabilities?
Yes, I mean, so all these applications, whatever we talked here, I mean, it's either machine learning or we have the drug discovery application today. I mean, even take a very simple example of weather forecasting. I mean, 15 years back, at least I have been observing that time, you will see a report saying it may rain. The word used to be may rain, but these days it has become reasonably accurate. If you take a look at any of the website, it says today it will rain, exactly around that time it will rain. So I think that is helping, not just for us, but I mean, agriculture, means harvesting the food, all kinds of things. It is helping. So this is having a lot of impact on society.
And one of the things that's happening too is we know that a lot of times single point simulations aren't, part of the reason they're not very, weather forecasts aren't so accurate is part of it's just because one point is really not enough. And so part of what becomes possible is more ensemble type of calculations, which make not just in weather, but in chemistry or other areas where you have a wide range of potential solutions. It gives you much more of an ability to generate those solutions quickly and have better forecasts, whatever the forecasts have to be, if they're weather, if they're molecular structure, or is there something else?
And even like a very simple example I see with my daughter these days, we do web search. She doesn't do. She just asks Siri any question. I mean, she opens up the iPhone and asks a question. Okay, I mean that is the kind of the expectation from the next generation. So in the behind the data center, I mean somebody has to operate on all these things, and millions of requests at this per second. So there is a huge need. There kind of things. This is where like the big data and HPC also coming together in a very common application or an interaction with human beings.
Yeah, I would say as far as flops, although traditionally we talk about flops as sort of the metric, I would consider anything that does exaops, whether floating point or not, it could be considered an exascale machine, and that could be a big data application that is just crunching integer data or any type of data type, just the operations per second. When you talk about real time, it's just another way of measuring performance, but you need a certain number of operations per second to do some real time workload. So, but I agree, we shouldn't get stuck on floating point, because there's a lot of different applications out there that now are not necessarily floating point intensive that we would still consider high performance. So, I think I sort of agree with the premise of what you're saying, that an exascale machine certainly doesn't have to be about, a traditional HPC physics simulation or something to be an exascale environment.
Though I do think the flops will play a role, because say we talk about IoT, we have sensor data. So it's not just like the Facebook type of computation. We are dealing increasingly, I believe, in the dominating form of the Internet of Everything.
Right.
There will be the physical that is plays, I would say, the growth is all the embedded devices and the monitoring and control of the physical world, not only the cloud side of the, let's say, consumer apps.
Yeah, and there is more examples, right? And I think there is a connection between the HPC and the big data analytics. And my perspective, it's pretty much using the same capabilities, and it's becoming one. Another example is solving traffic jams. Today you're trying to avoid traffic jams by putting a route, and the Waze or any other application try to avoid you getting the traffic jams. But essentially in the future, if you put or get information from every person and you know the route before that person starts the trip, it's just a simple matter of routing, and then you can essentially eliminate traffic jams at all, right? So there is more things you can solve in the future by getting those exascale capabilities, but with the ability to crunch data in a very, very fast way. So I agree with you.
Yeah.
Maybe we need to bring as closer all these examples to HPC. The problem is still, every time we're talking about the big data problems, it's not in the HPC feed. So we'll always take examples of the traffic, of the PayPal, of the Facebook, of YouTube. And these are trying to solve outside the HPC or in their own, not in the community of the HPC. And that's where data analytics, and if it will come as close as possible to the compute where it get analyzed and get results from it, that's what it must be gaining a lot from the power of HPC.
Yeah, and another example I can cite, some of you might have already heard of, like this is the hurricane season when it happens in the East Coast. They actually use, it's the accurate modeling of the hurricane path. They try to do using HPC machines and as well as flying aircraft on the top, and through that they exactly predict how it will go, and then they give like people 24 hours, 48 hours notice to either to evacuate or to harvest the crops or tell the airlines to move all your aircrafts. That has a big societal benefit. If you don't do those kind of things, you will see a lot of damages happen, and so those kind of applications are again coming where you can do real-time analysis, and And there again lies a lot of good examples for Exascale. Together with the data, the data may not be big data in a traditional sense, but those are very valuable data or important data.
Okay, but one more question here, just from a time perspective, and if there will be another question here, we'll take it too. So the last question from my side is, in your perspective, how should we lead toward Exascale? In the sense of, do we want to drive more open systems or open technologies or open architectures out there? Do we want to create more standards around that, or have companies create their own proprietary elements and try to get us to Exascale? What's your view here from a general perspective on the major path towards the Exascale? And I give you one example. If you're looking on hyperscale, which also dealing with the same scale, different views, but one example from Facebook is establishing OCP, which is bringing standardization into hyperscale in order to create more solutions, in order to reduce the cost of those solutions. In my opinion, if we can keep the academic or the labs, the government labs, close to what the industry is doing, and having the same solution being used for both, that's a good options to reduce cost of things. I think clusters was a great example of something that can be used for both, and that's why it's cost effective. But that's kind of my view. But interesting to hear your view. Should go proprietary, to go Exascale, have open systems, create standards. We don't need standards.
I mean, the open standards always help. I mean, so whether it is a hardware or software. In fact, in my talk, I just indicated like the Infinima and how it has evolved over the years, mostly through open fabrics. That was the software stack. It initially started with OpenIB, and then Ethernet people also joined. It was renamed as Open Fabrics. And just like the example I showed, how the clusters are becoming very prominent, and it is a software, Open Fabric software is playing a big role. I mean, so people are a part of it, a lot of organizations are part of it. So that kind of standardization always helps to bring everybody's effort together, so that as a community we can grow much more faster.
So I have a little different take on it. I think there's always sort of a tension between innovation and standards. And usually at the beginning of a technology cycle, you want more innovation than standards. You mentioned the hyperscale and the open compute project. That came out as an evolution of what these guys were doing. It wasn't the first thing they thought of when they built their infrastructure. They said, okay, we're at a mature enough level, we have to standardize what we're doing to cut costs. To build the first exaflop machine, they don't really need that. And what we've seen is sort of a variety of architectural approaches, which I think are going to continue in parallel between, at the network, storage, and processor level. Everybody sort of has a different idea, and I think that's okay right now to have that innovation and sort of diversity, let's say. But as you get into the exascale era, the next decade, I think you'll see standards kick in where they should when things mature and they need more efficiency and they want to stimulate the software development environment, that sort of thing. So I think there is that tension.
So we'll make just a short comment about standards and commodity. Actually, we reach now, the level of technology reached now these days thanks to the commodity. And standards now, but we got the commodity driven. They were driven by the community hard because there were some customized technology challenging them. So both of them are fundamental. So we need the customized challenging technology to motivate the commodity to move forward and work harder. So that's why they should always go in parallel. That's also applicable to the software, where we'll have the open source as an alternative for every software solution available that gives it a real difference in the software environment that scales at these certain levels, where then the open source community will work harder to be able to achieve close to the industrial.
Okay. Anyone else wants to comment? Ask the question. So my last comment here, Michael, there are solutions or technology that started from day zero as open collaboration, which are important. I think Linux is one example. That started as a open collaboration day one and didn't really, went to companies to create closed solutions. There is other examples of other, I think NVMe is another one, right, which essentially might be able to drive storage. It's also started as a collaboration more or less and not letting. In my personal opinion, no one will reach Exascale by its own, and it does require collaborations. As the more open collaboration exists out there, that will enable other people to go and use the same technology for other things. So if we get to something that will be used for hyperscale as machine learning and be used for the traditional HPC and will be used for big data and other things and will be common, that will create the capabilities of scale or the power of scale, which will reduce cost and price associated with developing those technologies. But that was kind of my view here. I want to thank the panel for participating, panel members for participating in the panel as well as presenting earlier today. Thank you very much.